In a controlled laboratory environment, an experiment was conducted under conditions designed to eliminate uncertainty. The variables were isolated, the instruments calibrated, the parameters clearly defined. Nothing about the setup suggested unpredictability. The goal was straightforward: confirm a theoretical expectation that had already been tested many times before. But when the measurements appeared on the screen, they did not match the theory, not slightly, not within acceptable marginal error. They exceeded it. The result was not noise, it was not fluctuation, it was structured, consistent, and according to the governing equations, it should not have happened at all.
Scientific experiments are built around predictability. When inputs are controlled, outputs should fall within defined ranges. That is the essence of reproducibility. The theoretical model guiding this experiment had been peer-reviewed, refined, and widely accepted. Its equations were stable, its predictions reliable. Yet the data displayed a deviation beyond theoretical limits. The first reaction was simple: check the equipment. Calibration logs were reviewed, sensors were inspected, environmental interference was measured and ruled out. Everything functioned within normal operational thresholds, and the anomaly remained. The experiment was repeated. Same lab, same instruments, same materials. The result appeared again. Not identical in every detail, but consistent in the key variable that violated the model. At this point, the deviation could no longer be dismissed as random fluctuation. Multiple measurement devices confirmed the outcome independently. Data logs from separate systems aligned. What was being observed was not a glitch. It was a pattern, and patterns demand explanation.
The governing theory predicted a strict boundary, a measurable limit beyond which the system could not operate. That boundary was crossed. According to the equations, the energy output should have plateaued. Instead, it increased.
The energy signature is off the charts.
The system behaved as if an unknown variable had entered the equation, yet no such variable was identified. If the data were correct, then the theoretical ceiling was incomplete. If the theory were correct, then the data must be flawed. But repeated verification strengthened the data, and that left the theory exposed. Researchers began searching for hidden factors, undetected environmental variables, subtle material inconsistencies, statistical misinterpretation. Each possibility was examined methodically. Simulations attempted to replicate the anomaly under modified conditions. The outcome could not be reproduced artificially. Yet in the original controlled setup, it continued to appear. The experiment was not chaotic, it was disciplined, and that discipline made the contradiction sharper. When experimental results contradict theory, scientific systems rely on replication across institutions. Other laboratories were invited to repeat the procedure. Most attempts failed to reproduce the anomaly, but one independent facility reported a similar deviation, though under slightly different parameters. The pattern was faint, not universal, but not entirely isolated either. This ambiguity complicated interpretation. The anomaly was neither confirmed broadly nor eliminated entirely. It existed in a narrow band between acceptance and dismissal.
Peer review discussions intensified. Some argued the anomaly represented experimental noise, amplified by rare conditions. Others suggested the theoretical framework might contain assumptions too rigid to account for edge behavior. The debate was technical, measured. No dramatic announcements were made. Instead, the paper documenting the results was published with cautious language, highlighting inconsistency without claiming discovery. In scientific literature, tone often reveals more than headlines. Over time, citations referencing the anomaly decreased. New research moved towards safer extensions of established models. Funding bodies prioritize clarity, predictability. An experiment that produces an impossible result introduces instability. Without broad reproducibility, it becomes difficult to integrate into textbooks. The anomaly did not vanish. It remained archived within journals, accessible, documented, unresolved. The deeper question is not whether the experiment was flawed. It is how scientific systems respond to boundary violations. Models are constructed to explain observed reality. When reality exceeds the model, refinement becomes necessary. But refinement requires confidence that the deviation is not accidental. In this case, the anomaly occupied a narrow margin, too structured to ignore, too inconsistent to confirm universally. That narrow margin became its resting place. The laboratory where the experiment was first conducted still exists. The equipment has been recalibrated for other studies. The anomaly remains part of the record. It did not collapse the theoretical framework, it did not rewrite the equations, but it introduced tension, a reminder that models describe reality, they do not define it. The experiment produced a result that should not have been possible. It was measured, repeated, documented, and then it settled into quiet uncertainty. The boundary was crossed once. The question is not whether it happened. The question is what it means when limits prove negotiable.